Hi, today we'll be talking about arc length. Let's start with deriving the special formula we have for computing arc length. So first we'll talk about the length of a line segment. And this is something that we should be able to compute. What is the length of L of a straight line segment from -1, 1 to 2, 3? Okay, so the way that we compute the length of this diagonal line is by using Pythagorean theorem, considering this as the hypotenuse of a right triangle. We know what the lengths of the legs are based on the y-coordinates. The y-coordinates are 3 and 1, so this side is 2. And the x-coordinates are 2 and -1, so this side is 3. So that means, using this computation, that L squared, this L squared is 13, which means L is the square root of 13. So computing the length of this curve, i.e. just a line segment, is quite simple. But what about computing the length L of a curve, given by the equation y equals f of x? Okay, here obviously we can't just apply the Pythagorean theorem, but we can approximate it by line segments and then use the Pythagorean theorem for those, right? So we have this right triangle and this right triangle and this right triangle. And at each step, we compute the change in x and the change in y. This delta symbol refers to change. Okay, and you do the same at each step. Change in x, change in y, and then use that to compute the hypotenuse. Moving right along. Okay. So we're going to try and compute the length of this curve using line segments that approximate the curve. Okay, when we take the sum over all of those line segments, we get L is approximately equal to the sum over x of the square root of delta x squared plus delta f of x squared. Okay, so here we're assuming that change in y is described by the change in a function value, delta f. Just factoring out delta x squared from that sum, so the first term turns into 1, and the second term turns into delta f of x divided by delta x. It's change in the f over change in x. And then, oops, this square should be inside of the parentheses. In the next line, we factor this delta x squared out of the square root. Okay, so instead of having delta x squared inside the square root, we have delta x outside of the square root. Okay, now we take the limit of this sum as the length of delta x, that change in x, goes towards 0. So we're splitting up into smaller and smaller line segments, and we'll get as a limit this integral, the integral from the smallest x value to the largest x value of square root of 1 plus f prime of x squared dx. Okay? And the same logic holds if we have x equals g of y. So if instead of having the curve be f of x, if we have, some curve which looks like this, x equals f of g of y, then we can apply the same reasoning. We have the square root of delta y squared plus delta g of y squared, and factoring out delta y squared, and then factoring delta y out of the square root, and we arrive at the formula integral from y min to y max of the square root of 1 plus g prime of y squared dy. See, it's very similar to the formula in terms of x, just replacing all of the x's with y's. Okay, now here's an abusive notation, and that's what mathematicians say when everything looks right, but it's not really formally correct. You haven't defined what you're really doing here, and we can't divide and multiply infinitesimals. So that's why this is an abusive notation. But still, it's quite a helpful way to remember this formula. So we're talking about our infinitesimal arc length, ds, and that's going to be equal to square root of dx squared plus dy squared. And that's based on the reasoning that we said before. We have a tiny change in the x direction, and a tiny change in the y direction, and that gives us an arc length of ds. If our curve is in terms of x, then we can divide through by dx to get ds dx, which is the derivative of s with respect to x, is equal to the square root of 1 plus dy squared over dx squared. And then you can get arc length by integrating both sides with respect to x. So s will be equal to integral of ds, which is just ds dx times dx. So this is integrating the derivative of s with respect to x, and then taking the integral of that with respect to x. Okay? And there should be some x min and x, or from start to finish. Start to end. There should always be bounds in the arc length problems. So you can do from x min to x max. Okay, and that's your formula for arc length. And you can use the same abusive notation to derive the formula for y. Just divide through everything by dy, and you'll have the derivative of s with respect to y is given by square root of dx squared dy squared plus 1. And then plugging that into an integral with respect to y, we get that s is equal to the integral of square root of 1 plus dx dy squared dy. Okay, let's compute some examples. Example 1. Determine the length of the curve x equals 10 minus 2y to the 3 halves from y equals minus 1 to y equals 2. So, just to get a quick sense of what this looks like, it looks kind of like one side of a parabola going from when y equals 2, it's about 15. Okay, and I'm scaling down the x-axis a lot, and when y equals minus 1, it's about 40. And so that gives us this curve. Okay. So looking at this equation, I see that x is given as a function of y. So I'm going to want to use the arc length formula, which states that L equals the integral from y min to y max of the square root of 1 plus dx dy squared dy. Okay, so let's start by computing dx dy. So this is given by, first you apply the power rule, and then you multiply by minus 2 because of the chain rule. So that gives us 3 halves 10 minus 2y to the 1 half times minus 2, which is minus 3 10 minus 2y to the 1 half. And now I want to be able to put in 1 plus dx dy squared into that square root. So let's do dx dy squared. And this is given by, well, the minus 3 turns into 9. And the other term becomes 10 minus 2y without the square root. And now I can plug that into our integral. So we have L equals the integral from minus 1 to 2 of the square root of 1 plus, I'm just going to distribute this, 90 minus 18y dy. Okay, so simplifying this a bit, this is the integral from minus 1 to 2, the square root of 91 minus 18y dy. And giving ourselves a new page. Oops, that was a mistake. Here we go. So we're still working on this integral. 91 minus 18y dy. And to compute this integral, we'll make a u substitution. U equals 91 minus 18y. So du is equal to minus 18 dy, which means dy is equal to du divided by minus 18. Okay, so we can plug that in now. We have, and we'll also want to plug in the new bounds. So we have 91 plus 18 gives us 109. And we have 91 plus minus 36 gives us 55. And now we have u to the 1/2 du divided by minus 18. Okay. So we can factor out the minus 18. If we want, we can use the minus, let's just factor out the minus 18. So we have minus 1 over 18 times the antiderivative here is u to the 3/2 divided by 2/3 or divided by 3/2 or times 2/3, where u goes from 109 to 55. And so we get minus 2 over 3 times 18 times 55 to the 3/2 minus negative, so that's plus 2 over 3 times 18, 109 to the 3/2. Okay? And to summarize this a bit more simply, this is 1 over 27 times 109 to the 3/2 minus 55 to the 3/2. Okay. So we found the correct form, we computed the derivative, squared, added 1, put it into the integral format, and then used a u substitution to solve the integral. Let's look at example 2. We're asked to set up but not to evaluate an integral describing the circumference of an ellipse described by the equation x squared over 4 plus y squared over 9 equals 1. Let's think about what this shape looks like. What happens when x is 0? When x is 0, we have y squared over 9 equals 1, which means y squared is 9, and that means y must be equal to plus or minus 3. So when x equals 0, which is on the y-axis, we have y equals plus or minus 3. How about when y equals 0? Then we have x squared over 4 equals 1, or x equals plus or minus 2. And connecting the dots, we know this is an ellipse, so it should be nice and rounded. Pardon this terrible drawing. Okay. So the thing that I want to observe here is that y is not a function of x and x is not a function of y, because you've got y values that are common to different x values and x values that are common to different y values. So what we want to do is cut a piece where y is a function of x or where x is a function of y. And I think we'll do that here. Let's just take this piece. So this will be the piece that we compute, and then we can use the symmetry of this ellipse to say, I'll just multiply that by 4 to get the full circumference. So we can say the circumference is equal to 4 times the length of this curve. Okay? And now let's compute the length of the curve. Well, this curve, so the curve is described by this equation, and we can solve for y in terms of x, right? We can have x squared over 4 plus y squared over 9 equals 1. Well, that means that y squared is equal to 9 times 1 minus x squared over 4, which means that y equals 3 times the square root of 1 minus x squared over 4. Okay? So this is the equation for our curve where x goes from 0 to 2. Okay? And we're going to look for the arc length of that curve. Oops. Let's take this to the next page. Okay, so let's compute the arc length of this. So to get the arc length, so because y is a function of x, we're going to take f prime of x, and that's going to be 3 times, okay, applying chain rule, we have a square root of some function here, so it becomes that function to the minus 1/2 times 1/2, so we have 3/2, and then on the bottom here we'll also have square root of 1 minus x squared over 4. But then by the chain rule you take the derivative of the inside, so that's minus 2x over 4, or minus x over 2. Okay, and putting that all together we have minus 3x divided by 4 times the square root of 1 minus x squared over 4. Okay. Now we can continue to manipulate this. We want this to be squared. So that becomes 9x squared over 16 times 1 minus x squared over 4. We can write this equivalently as 9x squared divided by 16 minus 4x squared. Okay. And now we're getting there. We have 1 plus f prime of x squared equals, well, I could just write 1 plus this fraction, but instead I'll try to write this as 16 minus 4x squared over that plus 9x squared. So that means 16 minus 4x squared plus 9x squared divided by 16 minus 4x squared. And that's equal to 16 plus 5x squared divided by 16 minus 4x squared. Okay, so when we want to compute the arc length that we're interested in, we have L equals the integral from 0 to 2 of the square root of 16 plus 5x squared divided by 16 minus 4x squared dx. And then just recall that c equals 4 times that. Okay. And there's actually no way to solve this integral. This is known as an elliptic integral, and there's no closed form solution. But using the formula for the arc length integral, we can get this integral expression. Now we have example 3. Let f of t be the function describing the arc length of the parabola y equals 2x plus 1 squared from 0, 1 to t 2t plus 1 squared. That's just the point on the curve corresponding to x equals t. We're asked to find a closed form expression for f of t. Okay, so let's quickly draw the parabola to get a sense of what we're looking at. y equals 2x plus 1 squared. At x equals 0, it's equal to 1. And at x equals minus a half, it goes down to 0, back up to 1. So we have this kind of nice little parabola here. And we're saying, what's the distance from this point to the point corresponding to x equals t? Okay. And this is just the same arc length formula, but instead of having an upper bound given by some number, it's now given by t. Okay, so let's use the same approach as before. Because y is a function of x, so we're going to use the formula that integrates with respect to x. Okay, so we're going to compute f prime of x. This is given by the derivative of 2x plus 1 squared, which is 2 times 2x plus 1 by the power rule, and then multiply by 2 because of the chain rule, which is 4 times 2x plus 1. Then we want to square that. So we get 16 times 2x plus 1 squared. And then the integral that we're interested in will be integral from x equals 0 to x equals t of square root of 1 plus 16 times 2x plus 1 squared dx. Okay, you could stare at this integral for a while and try and figure out if there's any basic u substitutions you could make, but unfortunately there's no great u substitution. What there is a decent trig substitution. Okay, and if you recall, the trig identity associated to 1 plus u squared, this is u equals tan theta. Because of the identity, 1 plus tan squared theta equals secant squared theta. Okay, so looking at our expression here, we have 1 plus u squared, where u is 4 times 2x plus 1. So we're going to sub that in. Let 4 times 2x plus 1 be equal to tan theta. Making that choice gives us 8 dx equals secant squared theta d theta, or dx equals 1/8 secant squared theta d theta. Okay, and now we're going to make the substitution. We're going to turn this into an indefinite integral for now, just so that the notation doesn't become burdensome. But we'll keep it in mind that we have to sub in the bounds later. So we're going to take square root of 1 plus tan squared theta times dx, which is 1/8 secant squared theta d theta. Okay, let's take this integral to the next page. So let's continue to simplify. We have integral of square root of 1 plus tan squared. This simplifies to secant squared, so the square root becomes secant. But first, let's pull the 1/8 out, and then we have secant theta times secant squared theta gives us 1/8 secant cubed theta d theta. Okay, secant cubed is one of these integrals that was computed in the book as an example of a trig integral which doesn't have a simple solution. I will include the antiderivative here without the derivation, but I encourage you to check the book for how to compute the antiderivative of secant cubed. This is given by 1/2 secant theta tan theta plus ln secant theta plus tan theta. Okay, and that should probably have an absolute value sign. Okay. and that would be plus c because we are still working with an indefinite integral. Okay, now we made our trig substitution as 4 times 2x plus 1 equals tan theta. So let's draw a triangle to represent that so we can convert back. So we have theta here, and we're saying that 4 times 2x plus 1 is the tangent, which means opposite over adjacent. So 4 times 2x plus 1, and 1 goes over here, which means that the hypotenuse will be given by the square root of 1 plus 16 times 2x plus 1 squared. Okay, so plugging that into our interval, into our, or using this triangle to compute these functions, we have first 1/16 times secant theta is now square root of 1 plus 16 times 2x plus 1 squared. And we're multiplying that by tangent, which is 4 times 2x plus 1 plus ln of the sum of those. So square root of 1 plus 16 times 2x plus 1 squared plus 4 times 2x plus 1. And then we can evaluate that from 0 to t, because that was the original formulation of the problem. We wanted to get it as an expression with t. Okay, so I'm going to use one more page for that. Okay. Oops. So evaluating at the endpoints, we get 1 over 16 times square root of 1 plus 16 2t plus 1 squared times 4 times 2t plus 1 plus ln, okay, basically the same expression but with a t instead of an x. 1 plus 16 2t plus 1 squared plus 4 times 2t plus 1, and now we evaluate at the other endpoint, minus, okay, so this first part is 1 times 4 times 1, so minus 4 plus ln of 1 plus 1, sorry, that should be, oh, I think I made a mistake here. So this first expression is 1 plus 16 times 2x plus 1 squared. This is actually 1 squared, so that'll be 1 plus 16, so that'll be square root of 17 times 4 times 1, which is 4. Okay, and let's just make that 4 times the square root of 17 to be accurate, or to be a little bit neater. And then adding to that the log of square root of 17 plus 4. Okay, and this is the closed form for this arc length function. Quite a complicated closed form, but we did get it. Okay, so in terms of how you approach these problems in general, the steps for these problems are as follows. Identify whether you're dealing with y equals f of x or x equals g of y. Then compute f prime of x squared or g prime of y squared. And be careful that you're taking that derivative correctly using chain rule and everything else you need. Then simplify the expression, square root of 1 plus f prime squared or square root of 1 plus g prime squared, and integrate what remains. unless you're asked not to integrate. What types of integration end up being used in these problems? For arc length problems, the integration always involves a square root. So either, in the first case, the inside of the square root will be a linear function, which means, for example, square root of 1 plus 2x. Then you can use a u substitution and apply the power rule. Alternatively, the inside of the square root can be factored as a perfect square, and then you can apply the square root and get an answer that you can integrate. The last possibility, you may need to make a trigonometric substitution. When you have a stubborn square root, a trig substitution like sine theta or tangent theta may help integrate, but don't forget to compute the appropriate differential d theta and include that in your integral. Okay, and that covers pretty much everything you should see in this type of problem. And with that, I think we'll end the lesson there. Thanks.